Today, I am excited to show you new space-time analyses that are now possible with your atmospheric and oceans data. With the upcoming release of ArcGIS Pro 2.5 comes enhancements to the multi-dimensional raster layer type, which now opens up your raster data to exciting space-time pattern mining opportunities. Today, I will explore these new capabilities with you by performing space-time analyses of fine particulate matter air pollution data. Pollution matters. Elevated levels of fine particulate matter, PM2.5, are associated with premature death, increased risk of cardiovascular and pulmonary disease, and according to the World Bank, cost the global economy over $225 billion per year in lost labor. Countries and organizations such as China, the European Union, and the EPA here in the United States have put in place policies specifically targeting PM2.5 pollution control. Asking ourselves how successful these policies have been and identifying still problematic regions is an inherently spatio-temporal question. Therefore, the space-time pattern mining toolbox in ArcGIS Pro is uniquely placed to answer these questions. NASA's Socio-Economic Data and Applications Center have published a rich global time series of PM2.5 data as rasters. These data, dated from 1998 to 2016, were collected using 3 Earth observation satellites and supplemented using ground-based measurements. I've downloaded the 19 TIFFs and have them here in ArcGIS Pro ready to analyze. The data providers have cautioned against using these data at the original scale because PM2.5 gradients cannot be successfully resolved at this resolution. Therefore, I've resampled the rasters to a more appropriate scale for a global analysis, projected them into an equidistant coordinate system, and loaded them into this mosaic dataset. The mosaic references the 19 underlying TIFFs and also shows us the extent and footprints of the data. The rasters themselves are not time-aware. However, the mosaic structure allows me to add a new field and assign each raster a timestamp. Once I assign these timestamps, I've been able to run the Build Multidimensional Information tool to fully time-enable my mosaic. I can now run the new tool in ArcGIS Pro called Make Multidimensional Raster Layer. This tool unifies the experience of working with multidimensional data in ArcGIS Pro. I'll input my multidimensional mosaic and click Run. Notice that the tool has automatically detected my 19 time steps of PM2.5 data. The new layer this tool has created doesn't look visually any different. However, I can have a look at the properties and see that this is a fully time-enabled layer, showing my 19 time steps and my time range. This layer type allows me to utilize a whole new suite of analytical tools in ArcGIS Pro. Now, I'm going to open a tool from the Space-Time Pattern Mining toolbox called Create Space-Time Cube from Multidimensional Raster Layer. Previously, in ArcGIS Pro, space-time cubes could only be created using vector data, so this tool opens up many new analytical opportunities for your raster data. I'll input my multidimensional raster layer and choose a path for my output space-time cube. I'll click Run. This tool doesn't create any new layer type in my project. However, it has saved a netcdf space-time cube to disk. Now I have this space-time cube, I'm ready to do some analysis. I'll open another tool from the same toolbox, Emerging Hotspot Analysis. This tool is used to find hot and cold spots, statistically significant clusters of high and low values in both space and time. I'll input the space-time cube that I created, choose my analysis variable. I choose to conceptualize my spatial relationships as my 8 nearest neighbors and my 1 neighborhood time step. I'll change the default for Define Global Window to individual time step in order to eliminate the impact of annual fluctuations and trends on the data. When this tool runs, first it performs a spatial analysis using the Getty's or GI star statistic to look for areas that have significantly higher or lower concentrations of PM2.5 when compared to the overall global concentration. It then looks at these hot or cold spots through time, using the Mann-Kendall trend test to see if there are any temporal patterns, such as a location always being a hot spot or always being a cold spot. Let's have a look at the results. I'll zoom to Southeast Asia, where I see many red regions here for parts of India, Thailand, China, and several other countries. These are persistent hotspots, meaning that for at least 90% of the time steps, these locations were hotspots and that there was no discernible upwards or downwards trend in the PM2.5. The paler red regions we see for much of China, Bangladesh, India, and other countries mean that these areas are intensifying hotspots. The pollution is getting worse. I see a large cold spot here in Mongolia, which is mainly consecutive and persistent. I also see a large cold spot here on the Tibetan Plateau, which is mainly diminishing. This means, although the PM2.5 values are low, the situation is changing here. Let's move now to Europe, where I see several cold spots in the north, and in Eastern Europe I see some hotspots which are mainly diminishing and sporadic. EU law limits annual mean PM2.5 concentrations to less than 25 micrograms per cubic meter. I can use the new temporal profile chart on my underlying multidimensional raster data to select polygons from my hotspot analysis result and chart their time series over time. I've created this chart for 4 EU cities. I've added a grey shaded guide area to the chart between 0 and 25 to represent the EU limits that I mentioned. The World Health Organization has even more stringent PM2.5 targets of 10 micrograms per meter cubed annually. This is also represented on the chart as the second grey shaded area between 0 and 5. We see that Oslo's been doing a great job with PM2.5 levels within even the World Health Organization targets for the whole time series. We see that Paris and London have been within the EU levels and towards the end of the time series are even approaching the World Health Organization limits. Milan, which we see here in blue, is located in the Po Valley of northern Italy, where pollution is high due mainly to transportation, and the pollution is constrained by the topographical barrier of the Alps to the north, making even the EU targets difficult to attain. Let's now move to an area of the world with a new hotspot. We see around Addis Ababa in Ethiopia that there is a persistent hotspot surrounded by a sporadic and new hotspots. I want to try and explore what is leading to this growth of pollution through space and time. I have an idea that this is related to population. So I've obtained population data for 2015 and resampled it to the polygon cell size of my hotspot analysis results. I also added PM2.5 data from the same year to these polygons. Now, I want to use the spatial statistics tool called local bivariate relationships to analyze this data. This tool allows you to quantify the relationship between two variables and map how these relationships vary over geographic space. The question I want to explore with this tool is whether there is a relationship between population in an area and the concentration of PM2.5 in the same area. I'll choose my input features, select my dependent and my explanatory variable. I'll increase the default number of neighbors to 60 and increase my confidence level to 95% or 0.05. I can use the rest of the tool defaults. When this tool runs, it calculates an entropy statistic in each local neighborhood, in this case 60 features, that quantifies the amount of shared information between the two variables. For each output feature, it finds the significance and form of the relationship between the variables. Let's now have a look at the results. If I click on a feature, I can see the structural relationship that the tool found in the neighbourhood surrounding this feature, and view exactly, in blue on this chart here, where the feature fits into the model. In this location, the relationship is positive linear. In this location, the relationship is concave. Note that the variable values on the axes have been standardized. The result of this tool makes me believe that there is definitely some positive relationship between population and PM2.5 in my area of interest in Ethiopia, although this relationship may not always be linear. Let's move now west to the green area here at the intersection of South Sudan and several other countries. Here, population densities are lower, and we see a negative linear or a convex relationship between the variables. Perhaps my theory of population driving PM2.5 only holds at moderate to high population densities. I can use the swipe tool to view the underlying base map, where I see that this area lies at the intersection between the forest and desert ecosystems. Perhaps there are other processes taking place at this location that are dictating the pollution levels. Let's finally move back to the whole world to view the results of our analysis. I see here that where there are statistically significant relationships between population and PM2.5, that these relationships are typically positive linear or concave. There are still some green regions where the relationships are negative linear and convex, indicating other processes are at play, and these regions require further investigation. It's been so exciting to share with you the insight I have been able to gain from this pollution data using the new raster, space-time pattern mining, and spatial statistics tools in ArcGIS Pro. I really can't wait to see how many domains that you, as the subject matter experts, can apply these tools to help gain insights from your raster data. Thank you.